Okay, good evening everyone. In this particular lesson we're going to do some calculus, namely some integral calculus, non-proof based. Now what we're going to do is we're going to calculate the volume of solids generated by rotating a particular bounded region about an axis, particularly a vertical or horizontal axis. Now I'll rotate the camera and zoom in and out during the lesson. I redrew this. Now here's this is number one, and these problems come from James Stewart's Calculus, chapter 6. This is section 2. Now this uses the disk and washer method. Now suppose that we take the region bounded by y equals x squared, the vertical line x equals 1, and y equals 0, which is our x-axis. And we rotate, that's the region right here. That's this region here. Now we rotate that region about the x-axis by in this particular problem. Now the solid we get looks something like this here. Now notice that if you'll observe real carefully, I'll move this camera closer here. If you'll observe carefully, we have, here's our solid, and we're going to add up the volume of these infinitesimal green cylinders, and that we're going to find the volume of adding up arbitrarily many of these infinitesimal little green cylinders. Well, we're going to take the limit as these cylinder sizes shrink to 0 and as we increase the number of these little green cylinders. Now, amplified, these little cylinders look like this. Now, if you'll go back and look at the graph, I'm going to move the camera in here closer so you can see. We're going to rotate this about the x-axis. Now, if you'll notice this little rectangle here, we're going to take this little, we're going to rotate this, and this little rectangle is going to become this guy, the cylinder, sort of a sideways cylinder. Now, if you'll observe that as we rotate this guy out, the height of this green guy determines the radius. The height of this green rectangle determines the radius of these green circles here. But notice the height of this green rectangle is, by definition, y equals x squared. So y equals x squared is the height of this rectangle. Hence the radius of this circle. Okay, so hence the radius of the radius for this cylinder, I amplified the cylinder here, is x squared. Okay, so I won't stay this zoomed in forever, but I just want you guys to go ahead and be able to get an idea of what we're doing. I'll move the camera back here in a minute, I promise. So we're adding infinitesimally many of these little infinitesimals. Well, we're taking the limit, really, to be more precise. But that's an intuitive idea of what we're doing. So let me move the camera back. Pardon me while I do this. Now, so again, y equals x squared, x equals 1, y equals 0. And I did two drawings of the region. My first one I wasn't really happy with. I put stripes around the region, but that's kind of hard to see. I'll move pardon me while I move the camera. Here's the region. Here's another drawing of the region that I put in green stripes. So moving back now, pardon me. Let's do, so we got this. Now we rotate. Now to do the volume, we need to integrate over those infinitesimal little cylinders. To do the sum we want to do, we need an integral. So we do the integral. Now recall that that for each infinitesimal cylinder, which I've amplified here, the volume is pi r squared times the h, which h is actually running horizontally this time. So in this case, it's pi x squared times h, but observe that this is actually very, very thin. I gave it a thickness so you could see it better, but this is actually really, really, really thin. So it's DX, and it may be more satisfactory if I drew it like this. I just found this harder to see though. But this is we'll just stay with the bigger one. So I drew a smaller one, but this isn't entirely satisfying. So we've got a dx, which is very thin. So the volume of this guy is pi x squared squared, because you got to square the radius, dx. So we integrate over these little volumes, and there it is. Okay. Now I'll leave now from here on, it's just easy combo of calculus and algebra. You just use basic integration and a little bit of algebra. You subtract your lower limit from your upper, and you'll wind up getting pi fifths, and I'll leave that up to you. I did sort of skip that part because I don't want to dwell on that. To me, the hard part is getting these things set up correctly. If you can get them set up, then that's great. And observe something really important that I don't think any calculus book I've read emphasizes enough is this. This little rectangle here, which is a little maybe hard to see from this little rectangle right here, excuse me, it doesn't, notice you can, if you do a lower limit rectangle, you can keep this little rectangle inside the region, inside our region of interest. So it doesn't, if you keep it a lower limit rectangle, it doesn't have to come out. And so it can be drawn, that little rectangle can be drawn where it doesn't come out. So we don't have to do a difference of integrals. We don't have to take away volume from volume. We don't really have a washer yet. So that's an idea I want to drill home to you, and I want you to really hone in on the fact that this little rectangle doesn't transgress the region. It's this lower limit rectangle stays in the region, and that's pretty important. And I don't think the calculus books drill that enough. When this thing, if we have to go through some go through some space that's not in the region, that's going to entail some subtraction, and I'll show you that in a minute. And one thing I want to emphasize to you as well, always start your rectangle, always attach your rectangle to the axis about which you're rotating, okay? Please, attach your rectangle to the axis about which you're rotating, which here is the x-axis. Furthermore, the variable we integrate with is always with respect to the axis we're going around, which we're going around the x-axis, so we integrate with respect to x. I probably should have pointed that out earlier. And if had we gone around the y-axis, we would have used dy's, and I'd have had to set things up according to d. Now, that's another thing. And so in fact, if you go around any horizontal axis, you're going to integrate via x. And if you go about any vertical axis, you're going to integrate with respect to y. It doesn't necessarily have to be the x-axis. If it's any horizontal axis, it's with respect to x. And for y, likewise, any vertical axis. So I hope that helps. And I wanted to just drill home the main ideas. And I'll get my finger out of the way here. Let me zoom out. So there's the region, and there's the solid, and we're adding infinitely many of these infinitely tiny cylinders intuitively. Really, we're taking the limit as they shrink, and we're getting more and more of them. But I won't fuss too much about complete precision here. But so there's your dx, and getting my finger out of the way here again. There's your x squared. Again, this is your radius of x squared. So thank you. I hope that helps, and I'll try to do more.